In this lesson we're going to continue to look at thermometers. Remember, in the last lesson we looked at liquid-filled glass thermometers, and in this lesson we're going to look at thermocouples and how they can be used to make thermometers that cover a very wide range of temperatures. Okay, so we're going to look at just the basic principles about how a thermocouple works, and first of all we're going to talk about something called the Seebeck Effect. And Seebeck discovered that if you place the end of a conducting wire in a flame, an electrical potential difference will be generated across that wire. Why does that happen? Well, you remember that the conducting wire consists of atoms which are continually vibrating, and in between those atoms there are free electrons which would normally carry the electricity. And when we heat up that wire, these atoms vibrate more, the free electrons will tend to vibrate more, and as a result of that they will tend to diffuse or migrate from the hot end of the wire to the cooler end of the wire. So you're going to get a diffusion of electrons along the wire. As a result, this end of the wire is going to acquire a negative potential, and this end of the wire in the flame will therefore be positive, and you will get a very small electrical potential difference, or a very small voltage across either end of the wire. A small electrical potential difference, or delta V. That delta means change in, so it's a change in voltage, change in electrical potential. Now, the size of this electrical potential depends upon the temperature of the flame, or the temperature of this end of the wire. So as that temperature increases, more energy is transferred to the atoms in the wire, to the electrons in the wire. They will therefore tend to diffuse more, so more electrons will tend to gather up at the cold end of the wire, and that will cause a greater electrical potential difference. So we can say that the change in voltage produced across this wire is proportional to the difference or change in temperature between either end of the wire. Now we can make use of this effect to make a device that will measure temperature. Okay, so we're just going to extend this a little bit further and see what happens when we heat, instead of just a single wire, when we heat a junction between two different conducting materials. For example, okay, we make a junction between two different metals. We'll call that the hot junction. And following the Seebeck effect, what's going to happen again is that electrons are going to tend to migrate or diffuse along each of these conductors. But what we can say is that because they're different conductors, the amount of diffusion will be different in each conductor. So in one conductor, the diffusion of electrons will be greater than in the other. Okay, that will always be the case if we're using two different metals. So let's just say in this conductor more electrons diffuse. Let's just make a note of that. In one conductor, electrons will tend to diffuse easier than in the other. Okay, so we've got electrons diffusing in both conductors, but this one will become more negative than this one. Okay, so this one will be less negative because the diffusion effect is less in this conductor. Now the upshot of this is that this junction will be at a greater negative potential than this junction. In other words, you will have between the two junctions, and this is the important thing, a potential difference. Okay, again we'll call that delta V. So for example, let's just say due to the diffusion of electrons along this wire, we got an electrical potential of minus 30 millivolts, and in this one we got an electrical potential of minus 20 millivolts. Then the electrical potential between these two terminals will be 10 millivolts. Now then, the important point here is that as the temperature of this hot junction changes, as the temperature increases, the electrical potential difference between these two cold terminals here will increase. So the interesting thing is that the electrical potential difference between these two terminals is directly proportional to the temperature of the hot junction, and that is a very useful property which we can use to make a thermometer. Okay, so if we were to plot a graph of the electrical potential difference between these two junctions and the temperature of the hot junction, T, then it would look something like this. Okay, so we've got delta V, and we've got temperature, and you get a relatively linear relationship between the two variables. Okay, so we can use this to make a thermometer. Okay, so all we've got to do is to obtain a graph like this, and then we have effectively calibrated this thermocouple junction here, and we can use that then to measure temperatures. Okay, so there's our thermocouple. That's going to be the hot junction, and that's connected directly to our digital voltmeter, and so we place this in a flame. We note the reading on our digital voltmeter. It may come out something like that, 80 millivolts. Remember, we've already calibrated it. We've got a graph showing the relationship with delta V and T, so we can use that graph to find out the temperature of the flame. Okay, that tells us that the temperature of the flame is, say, 500 degrees Celsius or whatever. Okay, so thermocouples are very useful for measuring high temperatures. They cover a very large temperature range. Okay, so typically, depending on the type of metals that are used for this junction, a thermocouple could cover anything between minus 250 degrees Celsius up to 1500 degrees Celsius. So a much larger range of temperatures than a conventional liquid in glass thermometer.